Okay, so today we're going to be doing a means test on comparing two different sample sizes. So let's go over here to this flowchart that Professor Frieden gave us about which test we should be using to determine the test of two means. So the first thing we're going to look at is we're going to look at our data. And so we have two different companies manufacture machine nuts via different methods. Are the diameters of these nuts different? Assume that the population standard deviation 1 and 2 are unknown, and test it using an alpha of 4%. Okay, so let's look at our little flowchart. So the first thing we're going to try to figure out is, are they independent samples, yes or no? So we know that they are independent samples because the two different manufacturing process for these two companies are different. So therefore we can say that no, the way that company A manufactures their bowls is not going to have an impact on company B. So now that we've determined they're independent, we're going to ask, are both sample sizes at least 30? They are. They're 40, actually. So now we're going to figure out, are both of the population standard deviations known? So the other day we said yes, they are known, so we did a z-test. And so, but now it said that the population standard deviations are not known, so we're going to say no. So the first thing we need to do is figure out, are both population standard deviations equal? Which is kind of a weird question, because if we knew the population standard deviations, then we would know whether they were equal or not. But we can do another test, a chi-squared test, to determine whether these populations, to determine the population standard deviations and whether or not they're equal. So let's go ahead and do that first. Okay, so we are really quick. So the first thing we're going to do is we're going to say there are two populations. One of them is all the nuts that have been produced by company A, and then the second is all the nuts produced by company B. And then there are two random variables, XA and XB, and then you input the nut and that outputs the nut diameter, which we're going to be using for our test. Okay. So if we scroll over here, you will see that right here we have our chi-square test. So what we're trying to do is we're trying to see if the variances between the two nuts are the same to determine which test we're going to be doing to see if the means are the same. So this is an intermediate step to determine how we're going to proceed with our statistics. So the first thing we're going to do is we're going to determine our degrees of freedom, which is 39, and then we're going to do our chi-squared. Test statistic, which is your degrees of freedom times your sample standard deviation divided by your population standard deviation, which Professor Frieden determined earlier, which was 0.0105 squared. And so then you'll do that for both of your standard deviations, which are already previously calculated over here. They are given to us using the var.s of each data set. Okay. Now with that, we're going to calculate the p-value, where we'd use our chi-square.dis.right tail. For the values, we would use our test statistic, and then also the degrees of freedom, and then times that by 2. The reason why we're timesing it by 2 is because we have a two-tailed test. Whenever you have a two-tailed test, you always have to double the p-value because you're only getting 1/2 of the bell curve. So as you can see, we have a p-value of 46% and a p-value of 96%. So clearly, our p-values are much larger than any alpha that we may use. We failed to reject the null hypothesis, and we're saying that because we're failing to reject the null hypothesis, which was that the variances are not equal to each other, then we can assume that they are equal to each other. So the reason why this test kind of works is because we're saying it's not true, so therefore we can assume that they're equal to each other for our purposes. So now that we've determined that our variances are equal to each other, then we can do our t-test with our estimate for standard error. Okay, so that'd be a t-test with the pooled estimate for standard error, which is this homoskedastic case up here. So as you look at this formula, it's kind of complicated, but I'll just walk you through it really quick. You're going to do the degrees of freedom of n1 times the variance of n1, add the degrees of freedom times the variance of n2. Then divide that by the overall degrees of freedom, which is n1 plus n2 minus 2, or for our case, that would be 78. And you'll take the square root of that entire thing. Then you'll multiply that 1 divided by n1 plus 1 divided by n2. And then the square root over that. So it's really not too hard of a formula. It looks a little bit scary, but then once you break it down, it becomes a lot easier. Okay, let's go back here to our example 1. So we determined that this is a two-tailed test. Perfect. Because we are saying that mu A minus mu B does not equal 0. So that means our claim is the null hypothesis. So I use the average in order to get the sample mean of A. And then you can use the count function to find the sample size, which would be your n. And then the variance would be the var.s. Okay? And then previously we were given alpha of 4%. Okay. And finally, for our critical t value, then what we're going to be using is our t.inverse.2t test with our alpha, and then our degrees of freedom, which is 78. It is not the 39 that we were using before. And so why is that? It's because we're not just doing a test on one set of data, we're doing a test on both sets of data. So that means we have to take into account all of the points that are in our data set. So that means our degrees of freedom, which was shown here, would be n1 plus n2 minus 2. Perfect. Okay, and then the next thing we're going to do is we're going to calculate our pooled standard error. And so what I'm doing in my scratch work is I'm doing this first half of the equation, which is the big square root, which is the degrees of freedom times the variance plus the degrees of freedom times the variance divided by the degrees of freedom, and then the square root of that. So if we go back here, I'll show you what that looked like. So I have my square root, then I did my variance of b times the degrees of freedom, the variance of a times the degrees of freedom, and then I divided that by the overall degrees of freedom, which was the 78. Okay, and then that gives you an answer of 0.01. Our pooled standard error was I took the square root of 1 divided by the sample size plus 1 divided by the sample size, encased that in the square root, and then multiplied that by the value I had above, which was the first half of that equation, to give us a pooled standard error of 0.002. So to calculate the test statistic, what we would be using is the equation for our original t-test statistic that we did in chapter 7, which was the sample mean of A minus the sample mean of B minus the population mean of A minus the population of B. And then all of that is divided by the standard error. But the thing we're testing is to see if the two population means are the same. So that means that the population mean of A minus the population B is 0. So that means we can take that entire equation that's set right there, the mean, the population mean of A minus the population mean of B, we can take that entire section out of the equation because we're assuming that equals 0 for our test. Okay? So I did that, and I got a test statistic. If you can see it, I did the mean of A minus the mean of B divided by the standard error. And then that gives us a test statistic of negative 66.6. So just to kind of give you an idea of that, our critical value was 2.8. So if you imagine a standard deviation in your head, and then you imagine the 2 at the very corner of the tail, and then just go all the way to the left, like off the screen, all the way to the left, it would be such a tiny, minuscule standard, like very far away. Okay, so if we transfer that t-test statistic into a p-value, like let me show you what I did, the t.dis.2t, with that, I got an error because it's so small. It's basically 0. So our conclusion is that we're going to reject the null hypothesis and say that the two means are different. There you go. Do you have any questions about that? Just go ahead and email me or call me, and then that's everything. Thank you.